so far, I think we had little problems from the technical side. Yeah. Okay, so then I guess I will wait for 1 more minute for the people to drop in last minute, and then I will give a quick introduction, and then I hand over to you. Yeah.
Okay, perfect. Thank you.
And then, okay, I need to wait for our technicians to give the okay that we are on YouTube, which is now. So, okay. It's my great pleasure to introduce Professor Frank Allgöwer as our next speaker. Frank Allgöwer is a highly distinguished member of the control community and received numerous prizes for his outstanding contributions to the field. His work is extremely diverse, ranging from model predictive control to network and nonlinear control, where he's equally interested in the theoretical foundations as well as the practical applications. A somewhat more recent research interest of him lies in data-driven control and how behavioral system theory can be exploited to derive controller synthesis guarantees. Now, this topic is well aligned with the lectures by Claudio De Persis and Pietro Tesi we heard last Friday. And we are extremely grateful to have such a fantastic speaker in our summer school. So please join me in welcoming Frank Allgöwer, and the floor is yours.
Okay, thanks very much, Tobias, for this very kind introduction. I'm also very happy to be here and to be able to give a presentation here at the summer school. I would have loved much more to be in Zurich to teach in presence. Then also a summer school makes maybe more sense than if we are sitting in the dark rooms in front of our screens and cannot really enjoy the summer. So thanks again very much for the kind introduction and for the invitation. So for summer schools, there are actually always 2 types of approaches that you can do. Is first, if you have plenty of time, you can give a tutorial, like teaching a lecture, introducing to the details, to the fine specifics of individual topics. And that usually is done very well. Here we have a fairly small talk. I was told 1 to 2 hours, and that I'm fairly flexible. So I'm already saying that here because I probably will use that flexibility, but don't worry, I will not overdo it. In such a short time, it makes probably more sense to give an overview, to introduce not to a topic in detail, but more to show the ideas, to present where the ideas can go to and how far you can push them. I think it makes especially sense here because you had, as we just also heard on Friday, a nice tutorial, a very long tutorial on topics that are very similar. So the approach here will be more a holistic view, showing you ideas, concepts, and how they can be used, and not so much going into the very details. So that also fits to what the topic or the contents of my talk is essentially the work of 3 of my PhD students, Julian Berberlich, Anne Koch, and Tim Martin. So the results I'm presenting are results from their PhD thesis. So what I'm going to talk about, or the perspective we are taking, is not on tools, how to do something with tools like machine learning or artificial intelligence concepts, optimization, whatever, but the focus is really the view on data. So we see as the change over the past that we have now much more data and easier data available for us that we can use for control. And here is a graph that you can see that was published by Seagate, the producer of those hard drives. And it's a projection of the amount of data created over time. We are currently at 2021, but this data is from 2017, so up to here, it's precise, it's past data up to there, it's a projection. But we see that the amount of data generated is increasing exponentially. So this is really a nice thing. We have lots of data available, and we should think what we can do with this data. And we all know of the great things that have been done in different fields, like DeepMind, ruining the Go game for many people. Lots of interesting things that have been going on, but those things mainly focus on the tools, namely artificial intelligence, machine learning, than on the data. The data is, of course, a necessary condition for them to have. And here you see, hopefully I don't see it yet, 2 phenomenal examples of systems that perform interesting dynamic tasks. to the left is a video from Boston Dynamics of a robot that is doing gymnastics. And on the right, you see a car from Waymo that is driving autonomously. And these are technological advances. And those technological advances, they both require control. And what we can see is that the technology is not really simple. So we really need to have very good tools. And we also need to have guarantees. We need to have safety guarantees in order to be able to deploy such tools. And that they are not working always, you can see from those little movies, also by the same companies. So the left is from a TED Talk, and you can see that the robot is not always performing well. And on the right, you can see also problems with self-driving cars that may happen and that we should definitely avoid. So here comes then the needs that we need from the control side. We need to be able to give guarantees. We need to be able to make sure that our systems, these complex systems, perform well. And that this is not always the case. I again show with a simple example from object classification with deep neural networks that I've also taken from the literature. So these are no results of ours. So, and you all know that. So on the left-hand side of each of those pictures here is an object that has been detected by or classified by a deep neural network. To the upper left, it's a school bus. To the bottom right, it's a dog that has been exactly classified. Now, if you distort those pictures only by a little bit, and that's the middle pane that we are seeing here, then we see on the right-hand side essentially no difference in the picture. But the deep neural network that performed perfectly before is now seeing in each of those cases something else, namely an ostrich. So it's obvious that something is not well understood here, and that is what we definitely have to avoid in the context of control. This is something that we do not really want to do. So what makes our systems then, if we control them, behave in this perfect way that we see on the left here, this nice gymnastics doing robot, and not in the way that we see on the right-hand side? It's, of course, methodology, mathematical rigor, theory, systems, and control theory that are leading or guiding us towards such behavior. So clearly, what we need is not only data, what we need is not only tools, we need to have methods, a systems theory, a control theory based on data that allows us then to make sure that we are going in the right direction and that we have systems that perform really well. And that is, of course, exactly the theme of this whole summer school. So I liked it very much when I got the email invitation. I thought, wow, that's a great topic. That's exactly the right view on things. Namely, we need a foundation and we need mathematical guarantees for a control theory that is based on data. And that is also the topic of my talk. So the focus here is on the guarantees that we want to give. So we want to develop systems and a control theory that achieves to give those guarantees. So again, with a little more detail, but still on the motivational side. So far, systems and control theory is a model-based systems and control theory with lots of different models that came up over time, Laplace domain, state space, and so on. We have lots of different models. And for all of them, we have very well established theory. That is the big plus that we have. And we have a lot of experience with applying them. And what we have is really rigorous guarantees when they work. But in this model-based world, we also have a drawback. Namely, if you have to apply your theory, you need to be an expert in the field of the application. So it's not enough to know control, you also need to know your system and you need to know the physics behind it. Plus, getting to a model is very difficult and very often it's not available. If you look at the whole process in practice, when you have a plant that you want to control and come up with a good controller, then the modeling will be probably 95% of your time the controller design in the end is only maybe 5% of the time that is needed to come to an interesting result. So model-based, it's great, but it has drawbacks. Now, on the data-driven side, we have a lot of advantages as compared to the model side. Namely, very often you can just learn something by showing the learning algorithm how things are done and letting them work towards guarantees. So and plus it's kind of independent of the model accuracy. We don't have a model and we have no unmodeled dynamics. So all these things that we have in the control field to deal with uncertainty and so on, non-existent on the model-based, on the data-based side. So what we have as a drawback is, of course, we have no real guarantees. That is really the limiting factor. Up here, this rigorous guarantees makes engineers sleep well at night. Down here, we have no guarantees. And we may have safety issues for real-world applications. So every once in a while, things go bad, and we know that they go bad. Plus, you don't really learn from your system. So you don't really, if you do something, it may work out in the end, but you have not gained much knowledge. So the goal is, of course, clear. We want to find a way how to get the two advantages together. So the simple application, then to get rid of the need to get a detailed model of our system and deal with model uncertainty, and to combine that with a guarantee, with the systems and control theory. So that is the big picture, not only of that talk, of the whole summer school, and I would say in our field, in the systems and control field, this is one of the big things that we are seeing, one of the big directions where people are moving towards combining those two things. So what are we having? We are basing everything on data. Data can be gotten from simulations. So we have a detailed simulation model that we have, and from that we produce data, or from real world experiments, so that we really do experiments and get our data from. What we have is input trajectories and output trajectories that we can measure. And those input-output trajectories, we now want to derive controllers, we want to derive analysis methods, systematic approaches, how to deal with the systems that are behind that, that is based only on the data. So the grinder that you see here, this meat grinder, is what we are looking for. We want to have the tools and methods that allow us to take data and transform into analysis methods, controller design methods, and later on into controllers. That is the goal that we want to have. So, and in that framework, not only what I'm going to show you fits, but everything in this whole summer school here fits into that picture. And what I want to now show you, as I said before, I want to give you essentially three different approaches, or three approaches, and show you how this can be done. Once for analysis, analyzing systems, then a controller design methods, which will be model predictive control, which, by the way, is a very popular approach, and both for the robot and for the autonomously driving car that I showed you before, MPC solutions are used, or at least typically used. And then a last one will be robust control. So I will essentially show you analysis and controller design, but I want to show you also two different perspectives. One is the perspective of the fundamental lemma that you, I'm sure, heard already last week, but I will nevertheless repeat very shortly what the fundamental lemma is. And then we want to use this fundamental lemma for the analysis of systems, and then also for the controller design, for model predictive control. And we want to do that for linear systems. And we want to also to look into how that could be pushed for nonlinear systems. And then we switch gears, we go into a completely different perspective and want to use robust control ideas instead of the fundamental lemma, and see whether we can also do something on the basis of data-based approaches. So this is our program. Now, for the beginning, the fundamental lemma. What does the fundamental lemma do? So we have a system that has input and output trajectories. We are assuming for the moment that we have a linear system. a linear system with state X, with input U, and with an output Y. But we do not know the system. So we just know there is a linear system behind. And later on, as I said, I want to show you also that things can be extended in a certain way, at least towards nonlinear systems. So we have a system, and now we want to see whether it's enough to have one trajectory. So if we have only data, an input trajectory leading to an output trajectory that we are measuring, can we use this data, this one trajectory that we have, in order to represent our system dynamics, to characterize everything the system ABCD that we do not know encompasses. So classically, this can be done. We know that it's possible because we can identify a system from our input-output data pairs and then get a system description and then work with this system description. Identification-based literature, a very old topic, very advanced topic. Lots of things are going on. But here we want to really use, want to try to find out or want to use an approach that does not take that step, that has many drawbacks, as we know, and many advantages also, of course. But we want to go directly from data to characterizing the system behavior without having to come up with a system description. And the fundamental lemma is based on a paper that is by now more than 15 years old by Jan Willems and co-authors, all of them very famous people from 2005. And it's set in the behavioral system setting, as was already said by Tobias in the introduction. A very interesting viewpoint that I'm not going to take. So we are just going to take the tool, but not the further methodology from behavioral system. And there they were talking in this paper about trajectories being, or systems being persistently excited. So persistently excited, what does that mean? So if we have data representing our system behavior, is this good or informative data? Clearly, if we have a linear system and we put a u equals 0 on our linear system, we get y equals 0 as output, and we are not getting any information out of that system. If you use a constant u other than 0, things may be slightly better, but we still definitely have not very informative data. And that is what this fundamental lemma is really going to do. It's characterizing when is data informative. So we have a sequence, or they, I should say, have a sequence of n time steps of a signal uk, and we do the same, of course, for our output. The input signal can be multivariable, so this m here is the dimension of our input signal. For simplicity, just assume m equals 1. We have a single input, single output system. And now this data, this single trajectory, is now arranged in such a way that we have a data length L. So what we are dealing with, or the main problem that we are dealing with in a data-based control theory, is that we do not have infinitely long data pieces. So we assume now we consider data length of L. And now we are taking this trajectory that is longer than L, this one single trajectory, and form a matrix out of that. So we take the first L elements of our input trajectories and write it in the first column of our system. So u0 up to ul minus 1. Then we shift everything by 1. So we go to the second element, u1, and now we give the same trajectory, but we add one element in the end. And so we continue like that, u2 and so on, down to the very last element of our trajectory. So essentially what you have is in the first row together with the last column, you have all the data of your system. But it's arranged in form of this Henkel matrix. What does that mean? We have all the other entries that are just copies of what we have in the first row and the last column here, and in such a way that we have on the, now I don't know the English word, cross diagonal, so not the diagonal, but the thing that is 90 degrees to it, you have always the same elements, u1, u1, u2, 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 and so on. And this is a so-called Henkel matrix from mathematics. So you have that matrix. And now Willems and co-workers have defined when is a data trajectory U persistently exciting. And they say a data trajectory is persistently exciting of order L if this matrix here, that is not a quadratic matrix, of course, it depends very much on the relationship between the L and the N, what dimensions that system has. But if this matrix has the rank L, so of the length of the time that we want to consider, then the system is said to be persistently, the trajectory is a persistently exciting trajectory of order L, and we call it just the PE. So now, again, what do we have? Why is this important? We have a system, and we don't know what the system description is. We just assume it's linear time invariant. It's of order n, and I will comment on the order whether we want to know that or whether we need to know that a little later. And we assume it's controllable in the sense that we have nothing should be hidden inside of our system. So, and if we now know that our input trajectory is persistently exciting of order L plus n. So this L is the length of the data pieces that we want to look at. That's our choice. And the n is the order of our system. And we have now this UDs and YDs, so the trajectories, and we form these Henkel matrices with these trajectories. Then we can represent all the trajectories of the system. So not only one trajectory, but all the trajectories by the following format, namely the stacked two Henkel matrices with the input and with the output multiplied by a vector alpha of the appropriate length equals to our input-output pairs. So any input-output pair of length L, so any input-output trajectory of length L is a trajectory of our system if and only if there exists such a vector alpha such that this condition here is satisfied. This is, of course, very nice because we have here an object, and that you have seen last Friday already very much and in great detail. So we have an object here that consists only on this one trajectory that we have. And in a simple way, we don't have to derive a model. We don't have to come up with a differential equation or something else like that. But we just have one big matrix that we have here. And now in the span of that matrix lie all our trajectories. That this can be true is, of course, kind of clear because our trajectories are shifts of the trajectories. And then in a linear system, any trajectory uy is just the linear combination of those shifts. So what we have is a purely data-driven system description, a characterization of all that is in the dynamics of our system. The proof, I'm pretty sure you have done that on Friday. At least I assume the if part is trivial, and the only if part is also not very important. Now, as I said before, this was given in the behavioral systems setting, and that's an approach that is to systems and control that is fairly complicated, and not so many people dare to work in that field. And as you can see from its publication up to all the very recent years, there were hardly any citations of that paper. But this is now exploding. And the reason that this is exploding is that we can exactly use that characterization here that they used in a different context, that we can use that characterization to represent our systems through data. So this is the fundamental lemma. We can form from one single trajectory a data matrix, which is a Henkel data matrix consisting of two Henkel matrices. And this representation with Henkel matrix times an alpha here, representing all our possible input-output pairs, this allows us then to represent the total behavior of that system. So any uy pair is represented by some alpha. And if you plug in any alpha, then we can produce any u pi pair that there is. So essentially what we have is a representation of the system that is now based on data, but not that we have to identify a differential equation from the data, but we just form from the data a matrix. And that simple representation now is a model. So that is a philosophical question. Is that a model or is that not a model? Clearly, it is a model because it represents our system. And it's also a mathematical model in the classical sense. But it's one that uses the data in a very straightforward way without having to have a methodological step in between. And now with this representation, we can do anything that can be done for linear systems with other models, because we can always represent the u's and y's through that equation 1 here. And equation 1 has the big advantage that there is no solution of a differential equation that is necessary in order to characterize the output of the system. So this is the real strength. This is the real power of this fundamental lemma. And now I want to show you with 2 examples. One, an analysis example, and then after that, a controller design example with model predictive control. I want to show you what can be done with this fundamental lemma. Just pushing things and not really going into details here, just giving you an idea how that works. And that is not the only thing how it can work, because as I said, this can be used for anything, this insight. And that insight is also not our insight. So we want to go here in the present a framework for characterizing dissipativity of systems from data. Now, why is that interesting, characterizing dissipativity? Everybody in the control field knows that. That's like carrying coal to Newcastle. If we have certain properties of our system that we know that this is the case, then knowing that the system property exists already gives us enough information that in many cases we can even design a controller for which we can then guarantees for the closed loop behavior. So just knowing the system property is enough for doing the controller design. You don't need to know even more. So we can even go one step further if you know just the system property, independent of that, whether it comes from data or from a model, then the controller design problem is at least part of the controller design problem is at least already solved. Just think of the famous L2 gain. So if we know the L2 gain of a system, or we know that the L2 gain of a system is smaller than a certain bound, then we can get a stable closed loop by using the small gain theorem. So we can easily stabilize such a system. We can, or at least not destabilize such a system if we know the L2 gain. Same for passivity. If you know that a system is passive, or how much lack or excess of passivity it has, you can come up with a controller as a suitable P controller such that your closed loop is guaranteed stable. That can be extended to many more things like conicity, which is a generalization, general dissipation inequalities. There again, the name Jan Willems comes up, and can be also further generalized to integral quadratic constraints. So this is all of interest, of course, for our systems theory. Now, what do we want to solve? We want to find an easily verifiable condition based on data, and in fact, based on only one input-output trajectory of our data. Just one trajectory, and we want to be able to verify and whether dissipation properties are satisfied. And we want to be also able to determine which dissipativity properties are satisfied. So we want to use for dissipativity the framework as was posed by David Hill in 1980. So you all know the characterization of dissipativity with storage functions. Here we use a slightly different approach, which is equivalent, by the way. So we say that an LTI system G is dissipative with respect to the supply rate pi, and I will explain in a second again say more about the supply rate pi. So this pi here essentially characterizes what property we are dealing with. Namely, if this condition here is satisfied, our UK YK trajectory pairs multiplied by the supply rate, the sum over that has to be positive for any R, so including R going to infinity. And that has to be satisfied for all trajectories, UK, YK, all trajectories that have an initial condition that is 0. Then we say the system is dissipative with respect to this supply rate. So the supply rates are matrices that are usually specified as this Q, S, and R parts. And depending on how you specify them, you get different properties. For example, if you use for the pi such a matrix here, then you get the L2 gain being smaller than gamma. If you use for the pi this 0.5 and so on, then you get the dissipativity that proves passivity. You can get conicity and so on. Essentially, not everything, but lots of properties of systems, really many properties of systems can be characterized by dissipativity. For example, also minimum phaseness of systems, lots of different properties can be characterized in this way. So we are only having finite horizon data. So when we only have finite horizon data, there is a chance that we can only give guarantees over a finite horizon. And I will relax that later on in the second approach that I'm going to use with a robust control. There we will be able to get rid of that. But here we define a system to be L dissipative. So just dissipative over trajectory length is L with respect to the same supply rate, if that condition now holds not for any R, but for R's up to length L. This is the trajectory length that we are having. So finite horizon data giving finite horizon dissipativity. And then, of course, you can represent that definition just with its highest term with the L. So now we want to find a way how to check L dissipativity from one single input-output trajectory. And we would like to have guarantees really to characterize it. So an if and only if condition we would like to have from such a trajectory, whether the dissipativity condition is satisfied. So the key here is that we have to satisfy this condition for all UK's YKs. So it cannot only hold for one trajectory. So we cannot just put in our single trajectory that we have, plug it in and check whether it's true. We have to prove, we have to have a means how to check that it's satisfied for all trajectories of our system. And now we use the fundamental lemma, because all UK, YK, all UY trajectories that we are having as they are given up here can be represented with the fundamental lemma based on the knowledge of only one trajectory, namely this Henkel matrices times this alpha vector, and we can just plug that in. So if we satisfy that for all, we use this definition that we had before, or this characterization of all the trajectories. And in that equation, we just plug in the UK, YK from the fundamental lemma. And this gives us this description here on the right-hand side with this QS and R matrices being exactly the entries in this pi matrix that we had before, but now written compactly in form of this Kronecker, with this Kronecker product that we are having here. So we can just plug it in and get to that equation that we have. So now we have a known property matrix, pi L. We have a known data matrix, and we have the unknown alpha. And for any alpha, if you plug in any alpha, then you get any trajectory of that system. So clearly we are almost done here, right? Because everything in the middle we know, and then we only have to satisfy that with the alpha, whether it's positive definite, meaning we have to characterize whether the big matrix in the middle is really a positive definite matrix. So this is the condition that we have. So if we plug that in, then that matrix has to be positive definite. But we have too many trajectories at the moment because we allow all the trajectories. So also trajectories that do not have an initial condition, but the condition only has to be satisfied for trajectories with initial condition x0 equals 0. So having to satisfy that condition is too much, asked too much, because it doesn't have to be satisfied for all trajectories, but only for those with x0 equals 0. So what does that mean now in an input-output data framework, that our initial condition is 0? So we know if we have a system dimension n, that if we plug in for n steps u equals 0, we get after n steps y equal to 0. So we know for sure then that our state is equal to 0. So that can be represented, or if we have the u and the y being 0 for n steps, then we know that our system has a state x equal to 0. So that can be represented through that matrix v tilde n here. So this is just a simple matrix with ones and many zeros in our system. And that is this matrix here, and where we can again replace the uy by our Hankel matrix times alpha, is a side condition that we have to satisfy together with this one. So this way we ensure, or we limit ourselves to trajectories for which only the initial condition is 0. And now if you have a positive definiteness condition with an equality side constraint, you can apply a form of Finsler's lemma, how to come up with a single characterization of that. And this is this big matrix here that we are having. So all known parts, so this is just this matrix with the zeros and one. This is our data matrix, and this has to be a positive definite matrix. And now we can easily show the following theorem, namely we have a necessary and sufficient condition, how to prove L dissipativity. We just have to form this big matrix here, in which we have only the property of our system, only the data, and a matrix that depends on the n. And I make a comment on the n, which we also don't know in a second. And this has to be positive definite. So if our system is L dissipative, then it definitely has to be satisfied. But if we have an additional persistency of excitation, guarantee for our input, which we can easily show with the Willems lemma, then we have a if and only if condition. So if you want to just prove that dissipativity is not satisfied, then you don't need this persistency of excitation condition. Only if you want to prove that it's satisfied, then of course your data that you are using has to excite your system in a sufficient way, and needless to say that you need this persistence of excitation, this assumption on the persistency of excitation. So the key is this is a very simple representation, right? You just have to check whether a big matrix is positive definite or not. So now this n that we are using here to characterize the initial condition, that the initial condition is really 0. Now we don't know the n typically. We just have data, right? And we assume it's a linear system of order n, but what we don't know our n. So what can you do? You don't need to know that. Just choose an upper bound on that. Just choose something very large for your system, and then you are on the safe side. So this is a very simple thing, even if you know nothing for your systems. Now, so far, we have the problem that we are talking about data that has no noise. And that is, of course, the easy case. If you have no noise, then everything is easy. Everybody who knows identification also knows identification without the noise is really not a real identification. So we have to be able to deal with noise. And in that framework, it's possible to deal with noise, but not in a very nice way. I show you in the second approach that I'm going to show you, or in the last approach, this based on robust control ideas, that noise can be implemented much more naturally and in a better way. But for the time being, we just assume that our measured data contains some stochastic noise epsilon, which is additive on our output. Now, if we have our data corrupted by noise only in the slightest way, then of course our Hankel matrix equality condition is not satisfied anymore. So that cannot be true anymore. So the idea is to relax the condition. And to relax the condition here on the side, not on the Hankel matrix, but to relax the condition on the side of our characterizing inequality for showing dissipativity. Namely, we are now not asking anymore that this matrix is positive definite, but that it's just larger than some small negative definite identity matrix. And that can be done. And again, I don't want to show you, have a look in the paper to show you, you can compute such a suitable gamma with methods as we know them from stochastic systems. And you can compute a bound for which it makes sense. And so you can use your measured data. You just draw a sample of your noise. From the sample of the noise, you compute that bound. And then we check the relaxed matrix condition. Of course, it's a heuristic. So here we have no guarantee anymore. So we are after guarantees. So that is a real drawback, but it really works well in practice. And I will show you later on that we can circumvent that this is not necessary here to go to heuristics, but you can solve that problem correctly. Now I want to show you how that can be done, not with one example, but with 500 examples, namely 500 random 2x2 multivariable systems with noisy measurements of 10% noise that were randomly generated in MATLAB. So I show you now 500 systems, and for those 500 systems, we want to estimate what is the L2 gain. And here you see that. So here are our 500 systems on the x-axis, and they are sorted such that the systems with the smallest L2 gain are to the left, and with the systems with the largest L2 gain are to the right. So sorted after the fact that we have computed the L2 gain. Now the true L2 gain of these random systems are the yellow circles here. So this we can compute. We generate in MATLAB the linear systems in an arbitrary way, and then we compute what is the L2 gain. So this is our ground truth. This is the true L2 gain. And now you see here in blue what would happen if we have a noise-free estimate. If you just assume that we have no noise on our data, then you get the blue curve. And you can see that in that case, it's a really good estimate. And the estimate is really excellent, especially for small gains. For large gains, then we have a difference between the true L2 gain and our computation of the L2 gain with this database method. Why is that the case? We have only trajectories of a certain length here. And if we have too large a gain, then that length is not sufficient. So if you would increase the horizon or the length of our data trajectories, then we can do much more with our system. And now you can also see if we have noise and use this heuristic estimate, you can see that the result does not differ very much. So we also get a very good fit for our system, even for characterizing the L2 gain, even in the case that we have noise, 10% noise on all those 500 systems. Of course, again, this is no proof. This is heuristics. So dealing with the noise is something that can be done, but that is no real guarantee. So let me wrap up. What do we have? So we want to characterize based on data alone properties of systems. To be very general, we use general dissipativity properties where we can show a lot of different properties of the system. And from that, we then, of course, have systems analysis. But in some cases, we can even do a controller design or verify the stability and or robustness of our controller in the closed loop. So we have the data, just one trajectory, and we have a very simple positive definiteness condition that we have to check. And then we have a guarantee on the system property in the noise-free case. And in the noisy case, we have some heuristic property, some heuristic approach that allows us to draw conclusions on the approach. So this thing is, we don't need a model, and it's computationally very simple to apply that. Of course, there are many extensions that can be done here. For example, extensions to IQCs that has been done already, to the infinite horizon, or at least giving a bound on the difference between the finite horizon, L dissipativity, and the infinite horizon. That can also be done and has already been done. Then you can also optimize over the weights in the IQC. But there are many more things that are open. And that is exactly the spirit of this presentation here. So I don't want to show you just a method and say that is the method, but show you an approach and say, hey, this is a look on this whole data driven systems and control theory development, where you can do a lot of things. Some have been done already, some others have not been done already. So this was analysis. Now it gets a little more interesting. Now talking about controller design, and I want to show you that within the framework of model predictive control. And as this is a data-based summer school, I'm not assuming that everybody here is familiar with model predictive control. Even so, many people, of course, are, but I will quickly recap what model predictive control is. First, we talk about model predictive control in the sense that we really have a model. And for the beginning, we limit ourselves to linear systems. Later on, we will go to nonlinear systems. So we have a linear state space description of our system, A, B, C, D, with input UK, output input U, output Y, and with an initial condition. Our goal is to stabilize a set point. And now the interesting thing in MPC is that we can also consider constraints. Constraints on our inputs, so that our inputs have to stay within bounds that can be fairly general bounds. In the linear case, they just have to satisfy some additional linearity condition. And we can also have bounds on states and bounds on the outputs of our system. Now, what is the idea of model predictive control? We want to use an optimal control problem. Actually, we want to use the optimal control problem that looking at the infinite horizon from k equals 0 to infinity, and over the infinite horizon, we want to look at a cost function that penalizes the difference from where we are in our system to our set point, and from our input to where we are at the set point. So if the set point is 0, then the input US would also be 0. So we have here a bar over our U's and Y's, namely because in MPC, we are looking into the future, we are predicting. So these are not measured UK, YK trajectories, but predicted trajectories at a certain time point. And over the infinite horizon, we want to minimize that. Over the infinite horizon, it's a difficult problem to minimize it, or actually it's in the linear case, not such a difficult problem if you have no constraints, because then it's the LQR controller. But if you have constraints, and in the nonlinear case, this is really a difficult problem that you have to solve numerically, and therefore we only looking at a finite horizon, which we also using this L here. So this is how far in the future we are looking, and we try to minimize that objective functional here. But the U's and the Y's are not arbitrary, but they are connected through our system equations. We assume that at the beginning, so at the time of our measurement, we are at a known place, and that we have constraints that we have to satisfy. And now the MPC algorithm is a repeated algorithm. So at every point in time, you compute trajectories over your future. So trajectories, L steps into the future. And then you solve this optimization problem that you try to minimize this objective functional subject to those conditions that you have. Then you get an input trajectory, an optimal input trajectory over this whole horizon, but you only apply the very first element of that input trajectory. Only one, and you throw away all the other ones. And then you let your system evolve in time by one step. You take a new measurement and you repeat everything again. So you do a repeated open loop optimal control solution for your problem, and you implement it in such a way that you get your feedback by repeatedly solving this problem. In a cartoon, this can be shown like here. So we have our time axis here, and we are at the current time. So this is to the left is the past, and this here is the future. We want to control our system over the infinite horizon in an optimal way, but we only look at a finite horizon. So I use the capital N here. That should be an L, and the T is a K so far. So I use that slide from a different talk. So we predict our trajectories at our current time into the future over our horizon. And then we try to find the optimal input that minimizes our objective fact functional, satisfies all the constraints. And now we are implementing the first piece of that optimal solution and throw all the others away. We just implement this first piece, apply it to our system, and then we measure again, and then we recompute the optimal input trajectory, now with a shifted horizon. That's why it's called a receding horizon or moving horizon method. And then you solve the problem again. Of course, the solution is not the same as the second step from the first one, because we only have a finite horizon. So this is like playing chess, right? So you look a couple of steps into the future. I don't know, you are all smart people, 20, 30 steps. You look into the future, you think about what your opponent is doing, what you want to do, but then you are only making one step, and then you let your opponent play. You're not revealing actually what you are thinking the next steps would be. And then your opponent, which is the disturbance in that case, will do something. And then you reconsider for your next step. You think again, 20 steps, or in my case, 3 steps into the future, what you want to do, and compute again and only apply the first input. So it's this idea that is behind MPC. Now, what are the characteristics of this MPC? It's the moving horizon implementation. We deal only with finite optimization problems. We have a nice time domain formulation. We can incorporate constraints, and we have our explicit system model, which we are going to replace in the database framework here, in order to predict the future plant dynamics. We distinguish between linear and nonlinear MPC. So again, notation here is slightly different. Continuous time, and before I was talking about discrete time, we still stick to discrete time, but you get the idea very easily. So we talk about a linear MPC problem if the model is a linear model, but that's not enough. So in order for an MPC to be a linear MPC, we also need a quadratic cost function, and we need linear constraints. And then the computation of the linear MPC controller is very simple, because you only have to perform a quadratic program. If any of the conditions above is not satisfied, but any of them, so not only if the system is nonlinear, but in most cases, the system is being nonlinear, is the reason that we have to talk about nonlinear model predictive control, for where you have to solve a nonlinear program online. So it's a very old idea that really goes back to the very beginning of the optimal control literature. And here is a quote from Lee and Marcus from their book from '67. And that is actually the reason why MPC, there is no patent on MPC, because MPC was first done in industry, namely by Shell Oil, and in France by a company called ETHZ. And they tried to patent MPC. So we would not be able to talk freely about MPC today if they would have succeeded. But in these patent cases, this earlier book by Lee and Marcus was used to show that this idea was already known at that time. So the application is very old. So beginning of the 70s, they published only much later. They applied it really in industry. So we are talking 50 years MPC application now. And but the understanding why it works and what are the problems and what have to be circumvented are came much later. Actually, only 20 years later, at the 20 years later, at the end of the 90s, people really understood why MPC is working and what is the problem of MPC. Now, one of the problems that we have in MPC, and this is what we want to address here in this talk, is that if you just apply that methodology in the model-based case, as well as in the database case, and I will even show you experimental proof of that. If you just apply MPC controllers generically, you have no guarantee that the closed loop is stable. So there is really no guarantee if you just use the plain vanilla MPC controller as I showed you. And that can be shown with very simple examples. It's not difficult to come up with such example. Here is one that we have from our student laboratory where we do teaching of control. It's a 4-tank system, a classical 4-tank system. Don't want to say too much about the system. It's a nonlinear system, has input constraints, has state constraints, has a fairly slow dynamics. It's essentially a boring system. Students are not excited to work on that system. Not much is going on in that system. And it's really not a system that is too challenging to do control. Now you can identify a model for this 4-tank system. And here I show you results for a nonlinear MPC actually. So we really identify a nonlinear model from that and then do an MPC controller. Again, I don't want to talk too much about the details here, but we have state constraints, which is essentially that the tank cannot be completely empty and that the tanks have a length, which is 28 centimeters, that we have the pumps can only pump things into the tanks and not pump out of the tanks. And we can just apply a controller that makes a lot of sense. And then we get the following results. And this is the levels in the 4 tanks using an MPC controller that makes a lot of sense. So that is not a tricky controller. So using 60 seconds as a time horizon. So this is beyond the dynamics of the system. So the system is faster than 60 seconds, 1 minute. And what you can see here is 2 curves. One is the gray curve, which is a simulation, and the black one, which is an experiment. And the experiment only runs until a certain point in time. And what you can see here, at this point in time, the level 28 centimeters in tank 4 is reached. After that, the tank, our tank in our lab is at its end. And so we cannot have the experiment any further. Otherwise, we would get a big mess in our lab. But in simulation, of course, you can continue and you can easily see that the MPC controller is destabilizing that boring system. So it's not an MPC controller that was designed to be destabilizing, but it's one where you can argue that it is really should be a good MPC controller, and it's not stabilizing that non-challenging system altogether. Now, of course, this all depends very much on the prediction horizon. You can increase the prediction horizon, and it still stays unstable up to a certain point in time. So for the experts among you that know MPC very well, then you know that if you extend your horizon long enough, then you get stable at a certain point in time, and you can even compute what that t should be. But here you see that not only for the 60 seconds, but also if you take 2 minutes, it's still unstable. It only gets stable after a certain time. Now, if we stick to this t equals 60, so that was destabilizing in the end. And if we add so-called zero terminal constraints, this is something that we will also do in the database case, namely that we demand at the end of all the predictions that the predicted state of the system is at 0. Only the predicted state. It will not go to 0 at the end of the prediction horizon, but that in the predictions the state goes to 0. Then this is called a so-called stability constraint. And then for this short horizon, we see that we get a stable behavior, and that can be proven. That is MPC theory. That makes it interesting. That's why people still after 50 years work on MPC, because you have to do something. You cannot just apply it. You have to do control theory in order to be able to guarantee stability. And that can be extended to much better stability guarantees. So to much better ways, except for this zero terminal constraint that, by the way, we can also do for database control. Now, MPC is a very established method. I showed you before that self-driving cars, essentially all self-driving cars are controlled with MPC. Lots of things also in the robotics framework are nowadays done by MPC. So not only in the chemical industry. So it's a very nice method, but a method that has one drawback, because we need a model. We need a model in order to predict the future of our system, and then we can solve. Then we can come up with a input trajectory, a model-based input trajectory that we can exploit, and also giving the guarantees for stable closed loop. There we make use of the model that is available, and this is exactly what we do not have in the database world. We want to assume that we have no model, that we have only a trajectory of our system. Now, the idea is essentially obvious from everything that I said before. In hindsight, of course, everything is obvious, but as I presented it. So we have a model. We can characterize the future trajectories. So this U bar, Y bar of our system with the prediction model that we now have through our fundamental lemma characterization. Now just the alpha has to be chosen in a suitable way. So given our data, we can form our Hankel matrices, and now we can optimize over all the alphas that then leads to U bars, Y bars, such that our model is satisfied, our database model is satisfied, and that our closed loop is then an optimal closed loop. So a data-driven MPC looks like that we have our same kind of cost function that we had before, and we have a model. Now the model is our fundamental lemma description of the predicted trajectories. We have an initial condition, and the initial condition is now, of course, an initial trajectory. We discussed that with the dissipativity before. So in order to be able to characterize where the state of our system is, we need to have the input-output pairs for trajectory pieces of length L to be at a certain point. And we can also consider constraints. So what you have to do essentially is the same as in the database MPC framework, just replacing the predictions into the future by our fundamental lemma prediction. But it's of course a model-free approach in the sense that we don't have to solve a differential equation, and we don't need a differential equation at all. A side remark that I, coming from the MPC literature since my PhD student days, up to now, output feedback MPC is still a very challenging thing. After 50 years of MPC, looking at output feedback MPC is very challenging in the model-based world. Here, we have naturally an output feedback characterization. So we get that essentially for free. So in this data-based MPC framework, we do not have to worry about estimating our states and what problems that introduces into our approach. Now, computational complexity is comparable to the model-based world because everything is essentially the same, just with minor adjustments.
Excuse me.
Yeah, please.
I can interrupt to ask a question. You just said that the complexity is comparable, but the problem is that this alpha here is as big as the number of experiments, I think. So actually, I think, I don't know, I have the feeling that a data-driven MPC actually has a big disadvantage, which is the more experiments you make, the harder your problem becomes. But what is your...
Absolutely correct. And please notice that I did not write the same or low or whatever, but I said comparable, and because exactly of that point. So it's really not identical. There are differences, but it's not something that is from systematically completely different, right? So we still solve the optimization problem. We have a different number of unknowns than we have before, right? We have a different set of site conditions. So it's not the same, but we have the same type of optimization problem that we have to solve. So it's comparable, not the same, not easy, not definitely not trivial, yeah. And there can be lots of things, and actually that is on my next slide also. So the idea is came up, at least to our knowledge, the first time was proposed in 2015 in the paper on the left-hand side here. So there the basic idea is, but really because it is not so trivial, because you need to do a lot of things. The paper by Jeremy Coulson, John Ligoros, and Florian Dörfler is really the starting point of being able to deal with systems like that, because they talk about exactly the computational issues in that respect, and also have very nice examples. So it maybe sounds easier than it is. It is challenging, but it can be solved. Deep MPC, deep C is a very good approach in order to do that. And essentially after that deep C approach, really this took off completely. So lots of different things have been going on. Also lots of different properties have been shown. Open loop robustness properties. There have been quite a few practical applications. where really we talk about experimental applications. And there are even extensions to nonlinear systems, to distributed MPC, to encrypted control, lots of different things that have been going on. So this is really something that is exploding. But as I said before, if you just apply it plain vanilla, you have no guarantee that it really works. That also holds in the database world. So what is needed is also an MPC theory. So not only just doing the computational, in quotes, only doing the computations in that respect, but you also want to have a way how to prove that what you are doing leads to a stable closed loop, to an optimal closed loop, and so on. And this is exactly what I want to show you now. So really that part, can we do this MPC in that framework that we discussed before, that we have a data-based model in which we solve our open loop optimal control problem in such a way that the closed loop is stable. And also in the database world, not surprisingly, why should it be different? The closed loop is not stable. Same four-tank system. Now the MPC, the open loop MPC, is solved with this database framework, and we get the same unstable closed loop. So even for that simple systems. So no difference, of course, in that respect. And if you are not careful, then like for model-based control, then you may not have a good solution for your closed loop. Now, that is the point that I want to make here now, but this can be done. So using this data-based framework, fundamental lemma-based, we can do things that are similar to what we know from the MPC world. Namely, I mentioned before, zero terminal constraints. So you enforce that at the end of your prediction horizon. And again, here in the state model-based case, you just assume the state is zero at the end. Now we need a whole trajectory piece to be at the steady state. We enforce that, we add that constraint, this artificial constraint, to our system. And then if you solve the optimal control problem with this additional constraint, then it can be shown that the closed loop is stable. So we can give system theoretic guarantees, and the ideas are really the same as in the model-based world. And the implementation is again simple. You just add those constraints to your system, but now the proof is necessary. And the proof can be done, and you can not only prove that you are exponentially stable, but also that you can satisfy constraints in your systems. Why is it not going? So the proofs are also followed essentially the lines of classical model-based control, but you have a couple of additional challenges, like for example, that the cost function is not strictly positive definite. Now, that is under the assumption that we have no measurement noise. But of course, in applications, you always have measurement noise. So we have both.
Sorry,
yeah?
A very quick question. So you say that when we add an additional constraint, then we can guarantee stable. So is this, if we are doing like this, is this kind of method complete? Which means that you have an input like that. So so let me say my question in this way. Do you it is, so would it be the case that you cannot solve any U for this constraint optimization problem, or you must be able to find one when you add this additional constraint?
This is a very good question. I didn't want to go into any details here, but in MPC we talk about feasibility, and also the original optimization problems, also with constraints on the U's and on the Y's, is also not guaranteed that we have a solution to this optimal optimization problem. It may be that there exists no solution, and that's called the feasibility requirement that we have. So even without that additional constraint, and what in MPC, when you prove that you have an asymptotically stable closed loop or stable closed loop, then you always have to prove that you have that you stick to your feasibility. So the repeated feasibility, if you have feasibility at one point in time, then you want to have feasibility. You want to prove that you have feasibility also in the future. It's called recursive feasibility. That's something that is really crucial. And now to your question, we are adding a tough constraint to the system, right? So that after our prediction horizon, the state has to be at 0 at that point in time. So that is really a tough constraint, and it may well be that now with this additional constraint here, our optimization problem has no solution anymore. So this is well known from the model-based MPC world, and that is a big problem. That's why also equality constraints are not at all popular. This is just a simple way how to prove things. So this can be generalized to less tough constraints for which you can also show things. Quasi-infinite horizon model predictive control is one of those approaches where you only need to be in a neighborhood of your system. But even there, you reduce the feasibility of your system, and you have to prove that the solution of your MPC problem is recursively feasible, and that can be done. And here we have to assume in that theorem that I'm stating that our problem has a solution, is feasible at the initial time step. So our initial condition that we are having cannot be too far away from our origin. Otherwise, with those constraints, it's not possible to go there. So excellent question, but that is something that is inherent to MPC altogether, and not only to data-driven MPC. And actually, it's exactly it's exactly the same on both sides.
Okay,
as I said, it can be generalized, the constraints.
Okay, thank you very much.
So let's get back to another problem that we have, right? So, and actually a really severe problem, namely that when we deal with robust data, with data-driven MPC, we cannot really assume that we have all our measurements exactly. So our data are corrupted by noise, both the initial data, so the data with which we form our Henkel matrix are corrupted by noise, as well as our measurements that we're getting at each step in time. And for the moment, or here for the sake of simplicity, we assume that we have the same noise bounds on those scenarios. And now the beauty is that we can show that the result also holds in that case that we have noise. And that is a robustness property of the data-driven MPC approach towards noise that is really very important, and that is really very nice. How is it done? It's done in the same way as you always deal with noise. So we know that our fundamental lemma is not exactly satisfied. So we introduce the slack variable sigma, and the slack variable sigma that allows us then to still deal with this equation, but we don't want the sigma to be too large. So we do a regularization of the sigma and include that term also in the cost function. Plus we do an additional regularization of the alpha of that value that we have there. That is also a trick that is very well known in the, for example, also machine learning literature, that this leads to better results. So again, this is not some idea that we came up with, but a regularization and the slack variable with which you can extend things. But now the point is that you can prove still things. Now, if you assume that your input data are persistently excited, that your weighting terms for this regularization terms are chosen suitably, and there is lots of details that you have to look up in the literature, that the noise bound is sufficiently small, and that we have no output constraint in the simplest case, then you can show a very nice result. So the set point can be shown to be practically exponentially stable. So we will not go exactly to the set point, but we stay in a neighborhood, and we can also have guarantees for the region of attraction of our system, which is essentially or exactly related to these feasibility conditions at the initial step in our system. So this is a very nice result. Just think about it. We just have one data trajectory that we have. This data trajectory has noise. We have noise in our measurements. We only have an input-output framework, so no state measurements that we are having. And nevertheless, we can prove that we have practical exponential stability of the closed loop in our system. So this is a very powerful and a very strong result that allows application of that method to very nice examples. This can be extended to have guaranteed output constraint satisfaction as well. And as I mentioned already before, this is something that is in a few weeks. We have the nonlinear MPC IFAC workshop taking place. And there we have a paper where this is extended also, that we don't have the zero terminal constraint of our system, but that we can do something that is known as quasi-infinite horizon control in the MPC literature. So relaxing this feasibility constraint quite a bit. So again, for the 4-tank system application, so that was the system that with a time horizon of 1 minute, 60 seconds was destabilized by an MPC controller, also by the database MPC controller. Now we want to stick to our horizon length of this 1 minute, 60 seconds. And we will show that with the same horizon length, we are now getting a stable closed loop. And here you see the trajectories of the system. So the red is the set point of the water levels 1 and 2, 3 and 4 are not shown. If you just apply the MPC controller without this additional zero terminal constraints, then you get this dotted curve of the system. So clearly we are unstable. If you add the zero terminal constraint condition, then you are getting to your true behavior. So we are starting at 0.4. We want to go to 0.75 or something like that. Yeah, here, whatever exactly the set point is that we want to get to. And you can see if you would go even further down to 0, have a completely empty tank, then it would not be feasible anymore. Coming back to the question that was posed before, right? So you need to be in a neighborhood, but that neighborhood doesn't need to be small, as can be seen in that case here. So it really works, and it allows you to deal with systems that are corrupted by noise, but you can still give guarantees and you can achieve a good behavior. So now the beauty is that using this robustness properties of this data-driven MPC framework, we can also show that we can go to nonlinear systems. So going away from linearity to nonlinearity in that framework. So what we have now is a nonlinear system that we are assuming to have. A nonlinear system where we have a couple of assumptions, sorry, a couple of assumptions that our F and H are sufficiently smooth, and altogether I'm leaving away a lot of the details that are needed in order to really show the different results that I'm now going to show you. But the idea should become clear. We also assume that we have input constraints in our system, no output constraints at the moment. So for this nonlinear system, we can now, if we have the system model, compute a steady state manifold, namely the whole set of input states and outputs of our system, which represent all the steady states of our system. Sorry. Clearly, we will later on assume that we do not have our nonlinear system. So we only have data. So those state manifolds cannot be computed, but we assume that they exist. And in fact, later on, we will make further assumption on that steady state manifold. So now what is the idea behind this nonlinear MPC framework? So given our desired set point, we want to achieve now that we have stability to the set point. But keep in mind that we do not know or do not assume that we know our system model. So of course, it may well be that our YS that we want to control our system to, that it is not really on the steady state manifold of our system. So it cannot be reached. So if we do not assume to have a model, then we can, under circumstances, not achieve the YS, but we can come to the closest achievable set point that is closest to our YS. And we want to now Our goal is to prove that we we can go to such a closest set point of our system, and that this gives us a stable approach to that set point. Of course, the problem is again the lack of knowledge of our system, so that we may pose a problem that cannot be solved. Here is the idea behind the approach. Now, what we want to do is we use our linear data-driven MPC ideas and exploit the robustness of that linear data-based MPC. So at a point t in time, we are predicting for the future the system behavior of our system for the time t, now based on the past measurements of that system. So we are not taking a fixed model, but we are just taking the past trajectory that our closed loop has taken, and then use that as a representation via our Henkel matrices in order to predict the immediate future for one step at that point in time. So using the last n data points in order to go one step further by predicting L steps into the future. So what we are doing is we are updating our prediction model online. So we are really using an online model, do linear computation, but adapt it all the time at the conditions that we are having. So that is a slightly more complicated, as I shown you. This is the approach that we have. So in order to be able to prove things, we are really, what we need is we need to stay in the environment of this steady state manifold here and move along it slowly enough. Therefore, we always make a control towards an intermediate set point that we are having, an artificial set point on our manifold. But I don't want to go into details too much here, but essentially say that we have to now solve online the same problem that we had before. So from the nonlinear case, we now have a linear data-based MPC in which we have a linear system description, but this linear system description on linear data, this red part, we are adapting in each step. So we always use the past trajectories of our system. So the computations is essentially the same complexity that we have before. So, but we need now two approaches, right? At the very beginning, we also need a model. So we need to initialize our whole MPC approach by generating data at the beginning to have some model description in order to be able to do the first prediction step. After that, it's the same that we have done before, just with the system being adapted at each point in time. So the assumptions in order to prove that we are stable is an assumption mainly at the beginning step that is necessary there. So for this initial part where you have to come up with the first model, you need a persistently exciting system, which is really a nightmare to come about. But a lot of things can be done and a lot of heuristics can be done to ensure that we really have a persistently exciting first step. And I show you in a simulation how that looks like. We need to have sufficiently smooth nonlinear dynamics. We have to have a convex steady state manifold, and we need an additional property. And I don't want to dwell too much on that. That is related to that we are staying and sliding close enough to our steady state manifold along. That involves such a theta here at the beginning. So at least for the initial few data steps, we have to make sure that this is satisfied. But then you can prove under these assumptions, and a lot of details are left out, which you find in the literature. And I will give you at the very end a QR code to a place where you find all the papers that are referenced here and where you can read all the details. Here, just the big picture. So what we can assure for the nonlinear system, that we also have practical exponential stability. So now a nonlinear output feedback MPC with noise. So something that in the MPC literature, in the model-based MPC literature, it's very difficult to come up with solutions. We have in the data-based world, we can prove that we have practical exponential stability, exploiting the robustness that we have before. So that is a very nice result. And of course, I want to show you also that this result is applicable, namely by looking again at this 4-tank system, which we all know is a nonlinear system because of the amount of water that flows out of each tank. I don't know what the English name is for that, Fassregel in German. So the amount of water that flows out is a nonlinear system, and actually coming up with a nonlinear model for that and doing a good problem in a model-based world is not such a simple way if you are doing a system identification approach. Here we can do that based on just trajectories. And so I show you 2 different things. One is a simulation, and the second one is an experiment at the real plant. For both, for the simulation, we use a model, but the model is not with the true system. So we can say this would be something like a second experiment that we can do. And we have now these 2 phases. One is the initialization phase, where we generate the data before switching on our controller. So this is the input to the system, one of the 2 inputs that you have. And here you see the excitation of the system at the very beginning. I did not talk about how to generate that, but that is the excitation needed at the very beginning to come up with the first description. And then after that, the closed loop is switched on. From then on, we do an MPC control. We want to go to the red line here, and what you can really see for the 2 water levels, the blue and the dash dotted line, for the 2 water levels, you can see that we reach the red, the set point fairly close. You can also see that we only get practical stability because we have measurement noise and so on. So we will not have an exact landing on our trajectory. Now, exactly the same MPC, not changing anything in that MPC, is now applied to the real experimental results. Again, starting out with our initial phase where we identify the model, but now things are completely different, right? So now this is a different model that we have, but you can see that again, we have a very good behavior where we approach our set point in a very good way after a very short time in our system. But the key message here, it's not just applying it, but we have a guarantee. We know for sure from the start that we will not be unstable in that closed loop, but that we have guaranteed stability. And as I showed you before, if we do not change our setup, if we do not use these results, theoretical results, then we may get unstable for our systems. So let me wrap up that part. So showed you that using the fundamental lemma, we can do an MPC framework for having a data-based MPC. And with this novel theoretical analysis tools that I gave you a glimpse at, we can do also an MPC control theory. So we can come up with schemes that allow us to guarantee closed loop properties, and that not only for linear systems, but we can also come up with nonlinear systems. I showed you everything for 0 terminal constraints. Everything can be done for quasi-infinite horizon type constraints also, with outputs and with noisy data. So lots of things have already been done in that framework. Extension to nonlinear system, I showed you a little bit. Having less conservative stability condition is this 0 terminal constraint quasi-infinite horizon, which non-MPC people probably found strange what I was talking about, but everybody familiar with MPC knows exactly what's going on. But lots of extensions can be done and are possible in that way. So now we have shown that using the fundamental lemma, we can lots of nice things. And especially we can come up with theory. We can come up with theory for analysis and for controller design of systems that can even be extended to nonlinear systems. Even so, the fundamental lemma is, of course, only available for linear systems. So strong result. But now in the second part I want to show you a different framework, completely different mindset, leaving behind the fundamental lemma, but now using robust control ideas. how you can also solve the problems. And in fact, this approach even has advantages as compared to the first approach, and not only one advantage, several advantages. What is now the idea? So we still have, for the time being, our linear systems that we do not know. A and B are unknown. For the remainder, actually, of the presentation, I will now assume that we can measure the state of our system as the output. That is only for simplicity of presentation. Everything can be extended to looking at the output also there, but then things get much more evolved in showing them. So for the time being, we are looking at inputs and states of our system, and we have now noise that acts on our system. And the noise now is not something that we are adding later on, and we want to get rid of it or deal with it in a robust way. But now the noise plays a much more crucial and inherent way. So we assume that we have knowledge of properties of our noise, and in particular that we have a nice noise bound. Now the idea is the following. So we are again having one data trajectory. So one input trajectory, u0 up to un-1. That generates us an output trajectory, a state trajectory that we can now shift by 1, which gives us our xk plus 1, right? So this is just shifted the x trajectory from our state trajectory. Now we also have the trajectory of our disturbance, and the disturbance, of course, we don't know either. So for the disturbance, we only know about. And now the idea is the following. We want to characterize, not knowing A's and B's, but what A and B matrices there are that are consistent with the data that we are measuring. So we have one measurement of the data, and now that measurement of the data with the noise is not produced by one A-B pair, but there are many A-B pairs that can produce that kind of data by just having different noises on our system. And now we want to say the sigma xu here is the set of all our ABs that are consistent with the data that we are measuring. So there exists a noise term such that we have such that the data could be produced from this A and B. So this is the idea behind it. So we are not having one AB and one representation of our system, but we have a set. And we want to characterize that set of possible A's and B's, and then prove properties, then have an analysis for the system, but now not for one system, but for the whole set. And we also want to do a controller design that guarantees us things for the whole set of systems. So that is the idea behind everything. So how do we characterize the set? Let's assume we have for our noise the following noise bound description, which is something that you can write down. And for example, this kind of condition here is contained in this noise bound condition. Now we can write down easily this characterization for our set xu, which is all the ABs that characterize our system. Namely, what we just do here is we plug into our noise bound, for which we know this positive definiteness condition, the D that we are getting. The D again was from our data. We have an x plus equals ax plus bu plus the D. You solve that for the D, right? Then this explains with your measured x plus x and u's in connection with the A's and B's. This gives you exactly this condition. So this is the D, this is the D as we have above here. So this is the characterization of all the sets A's and B's that now relate only to our X star, U star. Now, the proof is very simple. Going in the AB's element X U's, then there exists, this is what I just said, and a disturbance that is consistent with our data, and that we plug into the noise bound. So these are if and only if conditions. Now we can resort that positive definiteness condition here. Just resorting it, taking the A's and the B's that we do not know, taking outside and leaving everything inside. So the PD here is our characterization of the noise level. The XU and X plus, just the shifted X, This is our data. So we have in the middle here a matrix that we know, and we need a positive definiteness condition now based on that matrix. Interestingly, this matrix here, this always has the same dimension for the system. So that is also an idea that not only we came up with, other people came also up with. Henk van Baarde, for example, used exactly that characterization to compute robust controllers, LQR, H-infinity controllers. But the idea is really the same in all those cases. Now we have a set of A's and B's that are consistent with our data that we can characterize. We have a characterization of this set that is based on data of our system. And now we want to show that for all the members of this data set, certain conditions hold. Now, this is exactly a robust control, robust analysis, robust control framework, right? So the idea is really we consider our ABs as uncertainty and now use robust control results. So in the robust control literature, we have this M delta structure now where our delta is the unknowns, but the unknowns in our case are not what we have normally in this robust control framework, but is exactly our A's and B's. So the model of our system, this is the unknowns. The knowns, this M in this M delta structure, is the form of our system that just describes that this relates to a differential equation. So if you plug the WK here up into this equation here, you just get the equations of your systems. So the uncertainty channel is this characterizations of all the ABs that are uncertain. And for that now, we want to use, or we can use, robust control techniques. Any one that you have, you can apply. Just using the same setup in robust control, just in a slightly different way, a slightly different interpretation, as I have shown you, and you can show different things. For example, we showed you before that dissipativity characterization can be something very interesting, namely that we want to have this characterization that this condition here is satisfied for all R for all positive R up to infinity. So the infinite horizon dissipativity characterization. And in the first part with this fundamental lemma, we showed you that we cannot really do that so easily. We have to go for a finite horizon characterization, and that the noise we cannot deal with so nicely. Here, noise is inherent, and we can write down everything for the infinite horizon from a start. And so what we now can do is use the previous results that I have shown you before, right? This characterization of our uncertainty and apply robust control ideas from, in the same way, modular changes that are needed. So it's not trivial, but with the tricks that we know from robust control, you can now come up on that basis in a result that allows us to characterize when a system is dissipative despite the noisy data that we have. And we have to only satisfy this positive definiteness condition. So a lot of steps have been omitted here. As I said at the beginning, it's not a tutorial in the sense of do first this, do second that, but the ideas are clear. We do a nonlinear approach and a robust approach, characterizing, trying to guarantee that for all our uncertainties, which is all the A's and B's, for which the true system AB is only one, but it's among all those ABs that we have. But for all the ABs, we want to satisfy our dissipativity condition. And for that, we can easily do by coming up with such a condition. So again, very strong result, and now much better suited because we have it for the infinite horizon and we have it for the noise. Let me show you again with the tank an experimental approach here. Now we only go for the 2-tank system, so not having 4 tanks, but 2 tanks. And what we are doing is we generate for these 2 tanks, we generate a trajectory. And here you see the 2 heights in the tanks, and here you see the input that is given to the system. So from a identification point of view, we would say, oh, that was not a very successful identification step. So we really have a fairly boring input and a fairly boring output to our system. But this is the only data that we will use. And we try to prove from that data that we are now having whether our system satisfies dissipativity conditions or not. And that can be done. So we also assume that we have noise on the system. And this noise plays, of course, a big role. So this is the assumed noise. So our data here have noise, of course, included. Not much noise, as you can also see, but we assume now different. We have to assume this noise bounds in our analysis. And this is the level of noise that we are assuming now. So at the moment, so what we want to do is we want to characterize for that system, for the two-tank system, what is the L2 gain? And we make different assumptions on the noise bound. Small noise bound, essentially no noise, very large noise bound. So here you see the magenta curve and the dash dotted green curve. That would be the L2 gain that you would get if you were to take the data and compute, do a parameter estimation or a least squares estimation and compute a system from that data. And then you just compute the L2 gain, which is those two curves. It's not exactly the same. Of course, we also make mistakes there. And it's, of course, independent of the noise because this is just our result. So the blue curve is now what we are getting with our robust approach. So clearly, if we have very little noise, then we have a very small uncertainty set. So there are not too many ABs that describe our system well. The true one is among those. And then, of course, we get to a result that is, as you can see, fairly close to what we could say is the true L2 gain. If you increase the noise level, then we, of course, also increase the amount, the A's and B's that are consistent with that, with our data that we have. So we have a larger uncertainty. And for the larger uncertainty, of course, you expect that you get a larger bound on the delta, on the gamma, so on the L2 gain. So if we increase the noise level, we get to larger and larger bounds. And if you assume too much of a noise, your uncertainty is too big, and then you will not be able to prove any level. And that is, for example, the case for those three last crosses here. So for those exists no L2 bound anymore. You cannot show any L2 gain. So if you have too large an uncertainty, your AB system's uncertainty, the class is too big, and you cannot show anything. On the other hand, we have the same here for too small noise bounds. So if we assume that the noise is smaller than 0.8 in times 10 to the power of -2, if we assume that, then we also get no result anymore. What is the reason for that? Now our data are not consistent with any of the ABs anymore. So we have not enough noise that describes our data, and we also do not get a result. But you can see that it works really as to be expected and quite nicely. You can do a lot of more different things. So for example, this is the input feed forward passivity that you have. So the lack of passivity that you have in your system that you could exploit in a controller design method. And you should see the same, what we would say could be a truth for the for this input forward passivity index, and what we get as a result from our data-based approach. And again, if we have too little noise, if we assume too little noise, then we cannot show anything because the data are not consistent. There is not any AB that is consistent with our data. If we assume too large a noise, then we also have no possibility of proving something like that.
Excuse me,
Yeah,
may I interrupt? So I am thinking of how do you choose the sampling time period? Here you chose 0.4 seconds, I think.
Yeah.
Yeah, here. So how did you choose this, and does this affect the result?
Yeah, of course. Yeah. So, but this is something that, of course, is not only a database problem, right? This is a problem of discrete time systems. And there is lots of knowledge available how you have to deal with sampling times for continuous time systems as we have them in reality. And the problems are exactly the same here. And you're absolutely right. The result is absolutely affected by that. And I cannot really give you a clear statement of that how that can be done. But everything that holds also in the model-based case also holds for the database.
Okay, thanks.
So let me wrap up. Yeah, please.
I do have another question. So about the set that you built. So you build a set with a linear model.
Yeah.
Is it how do you guys do that? Is it like an identification procedure?
No. That really this set is computed with our noise bound. So we use exactly what's given here. So we assume that we have a noise bound. So this was this omega bar in the example that I showed you.
Yes.
D bar here.
Okay.
Right? So we assume that we know how big the noise is, which is again, something that we do not know, of course.
But
so
you also assume that you have the knowledge of AB matrix. Like,
no,
in a deterministic way.
No, we don't know AB. No, that is the key. So we only assume that we have a noise bound. We only assume that we have the measurement of one trajectory, U, X. So the U, the X plus is shifted. The D, we do not assume that we know, right? So we only assume that we have the U and the X in our system that we have measured. We only assume that we have the noise bound. This is this PD. And now we are plugging the computed D from the previous slide. So just taking the data here and compute the D from that in there. And then we have a characterization where we now have the A's and B's included and reorder that into that form. So we have a positive definiteness condition that has to be satisfied for any A and B. So if this is positive definite, if that the inner part, if you want so, is positive definite, then we know that these ABs, they are characterizing all our systems. So no, we don't know. We don't know. If we would know the A and Bs, then it would be not a database approach.
Yes,
right?
yes.
And it would be a model-based approach. No, we have a characterization. Look at the equation here, for example. There we have only the unknown matrix X. So this is the matrix solution that we have. The pi is our supply rate that we have. Then the P down here is a matrix that is related again to our system. And then we have the C's and D's. This is the only thing that we have here. This is for the input-output case. In the state case, you don't need that. So here we assume the C and D are known. Nothing else is known. No A and B is known. Nothing like that.
But how do you compute like B, not knowing A and B? So that's
how do you compute what?
Like the matrix B, because from the set that you build, because we have an inequality.
I have not given here what the P is, right? So, but the idea is again, maybe I explain the idea again. So we are only characterizing which ABs do satisfy are possible ABs that can satisfy all the trajectories of our system that are consistent with the noise bound.
Okay,
so we do not know A and B. So it's a set, really a set, and we know the true system is in that set, but we do not know which member is. There can be many A's and B's that are consistent with the data that we are having. And this characterization we can do with this positive definiteness condition. That is the key. That is the basis for the computation. And from that, we derive then, using robust control ideas, we can derive anything. You can also do a controller design on that basis. I show you that in one of the upcoming slides. So no, AB is not necessary to know. So we just we use only the possibility to characterize the set of all A's and B's that are consistent with the data under the assumption on the measurement noise. And on that, you can do a lot of things like Van Waarde and so on. They do a controller design on that basis. Now, that can be also extended, and that is what I think is really the beauty. Can be extended in two directions, and I'm now running at the end of my time. So I'm going much faster now, just giving you a very rough idea. So very often, it's not a question that you want to use either a data approach or a model-based approach. Very often you have both. You have some model assumption and you have data. And why should you be restricted to choose from the start which one to use? You want to combine the two things. You want to combine your knowledge that you have from your model, that you know from partial modeling of your systems, or some uncertainty description for your system, plus any data that you can measure. Like, for example, in this simple mass spring damper system, we might know that the system has this form, but we don't know the A, B's, and C's. We only have bounds for the A, B's, and C's. And then on top of that, we can have data that allow us not then to identify the A, B's, and C's, but that we want to have in one step, use both at the same time in order to characterize properties or design controllers. Now, we use obviously exactly the same framework. Now we have more uncertainty, right? We have our unknown system, plus we have the classical unknowns that we know from robust control, namely, for example, parameters and so on. So we can have a lot of different setups with special cases. The one being the data-driven part, where our data is just delta is just the unknown matrices, A and B, in the case of just state outputs. And we can have, as a special second case, we can have the case where we have no data, but just any delta as we know it classically from robust control, or the combination thereof, so that we have knowledge about robust control formulation of a model plus data ahead. And now we can use, of course, that same framework, that same ideas, and we can again characterize what is the set of all possible uncertainties, now not only the A's and B's, but also the parameters in our system that are consistent with our data, and that give us a characterization that is given by the uncertainty knowledge that we know on the classical system case. So we have a combination of all these kind of things, and now you can come up with a theory that encompasses both. And again, you have a look in the paper for details. The reference is given in also at the very end. Now I want to show you an illustrative example for that. A simple academic example. The model, we assume not that we know it in our approach, but this is the model for which we generate our data for. Second order system, and our goal is now to do a controller design, a robust LQR design for that system. We want to achieve an LQR cost function that is as low as possible. We have a certain data length and a noise bound of our system. And now I'm going to show you three scenarios. One where we use only the data, so only the ABs are known, and we have data measurements, and we want to characterize what is the LQR design giving us the lowest cost. So this is essentially what I showed you in the past. The second one is a classical robust control approach. Namely, we assume that we know our system model except for two parameters, the 0.4 and the minus 0.3. And we know only that the A squared plus B squared is smaller than 2.8. So classical robust control, no data involved. And we do a robust LQR design for that step, which you can do. And then we want to combine the two things together. And this is the curve that is shown. So let's discuss first the classical approach. The curve is again the same as before. We take the noise level as the variable that we plot here. Of course, in the practical application, you choose one, and then you get just one cost that you can achieve. Now, for the classical robust control, of course, the result is completely independent of the noise level that we have. This is the red curve. So the cost is 70, 72, or 73, something like that. That is the best cost that you can assume if you only know that the A squared, B squared is smaller than 2.8, and then you can guarantee that the true cost is smaller than 72. If you do the same with our data-based approach, then we get this blue curve here. This is the same as we had before, right? If you have very little noise, then you get a very good controller because the uncertainty in your system is small. And then you get a much better controller, as in that case up here. If your noise is large and it's growing really rapidly, if the noise goes large, then you have the drawback that you have too many AB matrices that satisfy your data because you have a huge noise on your system. And now the black curve down here is if you combine the two. So if you make use of the data that you measured plus the knowledge about your model, and you can incorporate that in your hybrid framework where you can deal with both. And what you can see here is, of course, that in the limits you are getting to for the largest possible noise, you get to the limit of what the only information that you have is the model-based case. And for the data case, the model plays no role. If you have no uncertainty, then you have you know what your A's and B's are. So you get something that is always below both curves that we have. So having more knowledge, data, and a model is, of course, something that gives you more information about your system and gives you a better controller in that case. So far, this was all for linear system, can be extended to nonlinear system also in that way. So for example, extension to polynomial systems is easily possible. Also to non-polynomial systems, if the non-polynomial part is structurally known, so you know that you have a sinusoid or an inverse tangent or something like that in your system. But you can also go to completely unknown polynomial systems. And looking at the time, I promised that I will not overdo it with the 2 hours. Then I'm not going to show you these results now, but jump to the very end. Okay. So jump to the very end. What did I want to show you here in this talk? I want to show you that we have for the robust control approach, we can also simply characterize system properties and do a controller design without making use of the fundamental lemma, just by treating the systems as uncertainties that have to be consistent with the data. And that also gives us strong theoretical guarantees, can be applied to linear systems, to combinations of systems with prior knowledge that you have, and what I did not show you, also to nonlinear systems. Again, many open problems in that respect, many things that are open. Now, the summary for the whole talk. So what I tried to show you is that if we have only data, no model that we identify from the data, it's still possible to develop a systems and control theory in order to analyze the system and in order to come up with controller design methods. And there is not only one approach how that can be done, but I showed you 2 approaches. One is the fundamental lemma, which is a fairly straightforward and I would say easy to capture approach that gives us nice results and allows us to do fancy things like MPC controller design techniques, and where we can even prove robustness properties that allow us then to extend everything to a nonlinear world. Now, the second approach, which I think is even more powerful, is that robust control-based approach. So completely different type of thinking. We try to characterize our system by something that we ask the question, what type of systems are consistent with our data? And then for all those systems, we want to show that we can analyze the system certain properties holds. And also we want to show that for our controller works for all the A's and B's that are in our system description. And we still can achieve a closed loop that works very well. So these are all initial steps, but we are only talking about few years of development on these systems and control theory, while on the model-based world, we have 50 plus 70, even more years of experience in developing a theory. So I think there is lots of things that we can expect in that direction. and that also go beyond the two approaches that I have shown you. As said, everything in my talk is related to the PhD work of my 3 PhD students, Julian Berberich, Anne Koch, and Tim Martin. Actually, Tim will be very unhappy if you tell him that I did not show you anything about the nonlinear approach in the end. And here is the QR code, again, for which you can find all those papers. Here are pictures of Julian, Anne, and Tim, whose work I presented. And this is the end of my presentation. And I barely made it with the 2 hours, 1 minute short. So thanks very much for your attention. I guess you all asked questions in between already. And
Okay.
So actually, I have a general question for all data-driven control methods I mentioned here. So very important requirement for the data is the PE condition must be fulfilled. So based on the fact that the PE condition is fulfilled, does the condition number also play a role in these methods? How does this number affect the methods? Because this also play a role in system identification methods. So I'm just thinking whether this number also play a role here. Thank you.
Okay, so it's actually a difficult question. It sounds easy, but it's a difficult question because it implies a lot of things. Of course, in any of the approaches, your data have to have sufficient information about the dynamics of the system. So this persistence of excitation condition only explicitly appeared at the very beginning of the talk. In the second part, it did not explicitly appear, but of course it's also there, because if you have data that do not contain the information about your system, then you cannot do anything. So persistency of excitation is something very, very important in no matter how you look at the problem, and also whether you look at a data-based approach or a system identification approach, as you mentioned. And yes, there are many, many questions related to persistency of excitation. And I'm first of all, I'm not really an expert on all of that. And I think the answer is there is no simple answer to all those questions. But persistency of excitation is, of course, important. If your data that you are producing is not containing the information about the dynamics of your system, then you cannot do anything. So no matter what approach you use, also for all the upcoming future approaches that you all will do during your PhD thesis and develop that are much better than the ones I showed here, then during those you will have the same condition. So sorry for not answering your question. I'm not a politician, but I guess that was an answer that would be okay for a politician.
Yeah, I'm just curious. So thank you.
Frank, I have a comment.
Sure, Marco, go ahead.
I do not know how I should raise my hand in Zoom, so that's why I lost myself. Sorry about that. So first of all, Frank, thanks a lot for this talk. That was quite enjoyable to me. I dare saying that Jan Willems would have been proud of hearing this, because this is really in the spirit of what Jan Willems have been teaching all of us. That is the behavioral approach, where instead of describing a system in terms of representation, a system should be better described in terms of the behavior that are compatible with the system itself. And as a matter of fact, I believe that when we teach our courses in the systems theory, we should probably pay a closer attention to Jan's teaching in terms of how a system should be described. And I really like the idea of using the fundamental lemma, where basically you boil down to describing the trajectories that are compatible with one scene trajectory. So basically from one scene trajectory, we capture the whole set of trajectories. And I dare say that Jan would have been proud of hearing that that idea has later on developed into a framework for control in MPC, for example. So instead of moving from data into a complete description, a model describing the possible trajectories and then down into the behaviors, there was a direct path from the initial data into the final goal. So I think all this is quite lovely. Still, I do have a fundamental doubt, which is, looming large above my head. And the doubt is the following. So we have data, and in the traditional approach, we do have prior assumptions. So we assume that the system is this and that, the matrices are this and that, and so on and so forth. To me, using the fundamental lemma is really so I would like to separate two levels, the conceptual level and the algorithmic level. At the conceptual level, using the data through the fundamental lemma is pretty much system identification. So I wouldn't say that this is taking a departure from system identification. This is system identification. You identify the trajectories that are compatible with a given trajectory. It's a matter of language. So the departure is not at the conceptual level. The departure is at the level of language that is used to describe the system. And here we are really coming into the language Jans was using, the behavioral language rather than the language of representation in terms of matrices. But still, we do have initial trajectory, and we identify all possible trajectories as described by the fundamental lemma. So it's a level of language. It's not a level of identification of the system versus the direct use or the use of data without identification. And what's looming large is that along this path, we use a lot of priors. So the presence of the priors is there. So pretty much like when we use the ABC, because the fundamental lemma demands that we know the underlying system, and as you said very well, just an upper bound to the order of the system, which is enough. But still, it's there, so it's present. So in other words, along that path, we are doing identification through expressing that in a different language, and still we are using quite a bit of prior knowledge, pretty much as what we do when we do traditional system identification. And as a matter of fact, Frank, I got a bit confused when at a certain step of your presentation, you first said in the model-based, there can be a problem in MPC with the stability, and the same holds true for the data-driven approach. And then you mentioned the four-tank system, because to me, there was kind of a mismatch between the two, because you are using the fundamental lemma, which was for linear systems, and you're referring to something that was intrinsically nonlinear. So in other words, that approach that was data-driven was not applicable to the example, because the approach is not data-driven as such. It's data-driven plus much more looming large and staying behind the scene more than in traditional system identification. But in conceptual terms, it's still there. And it must be fulfilled, that assumption that there is a system A, B, C, and so on and so forth. Otherwise, the fundamental lemma doesn't hold in the first place. So it's, again, back to my very first part, Jan Willens would be proud of that. And I am as well, because I love it. I love it. Frank, no questions to ask, I love it. The idea that you come here and you say, okay, let's start from data and let's do system identification the other way, because we're interested in the behaviors. Why should we go to the upper level? And we all know that this is haunted with a lot of extra effects like the non-uniqueness of the representation, the ABC representation. So let's get rid of that. So go this way.
Okay.
However, a fundamental point is that this does not completely unleash the power of data, because the standard assumptions that are in system identification when you go the indirect path are still looming large over the whole framework. So, I mean, this was just, but can you comment on all this?
Yeah, definitely, Marco. So thanks very much. That was easily the longest question I ever got in my life. That was half.
It was more a speech than a question. Sorry.
It was also 4 questions. At least I think there are 4 questions in your question, and let me try answer them. But I cannot really answer them in a precise way, because I essentially agree with most what you say. First of all, Willems. So would Jan Willems be proud of what we are doing here? Well, everybody who knew Jan Willems knew that he was the most critical person that you can have. And I'm pretty sure if Jan Willems would have been in the audience, he would talk about mathematical details I didn't get right here. So that whether he would be proud or not is another question. But what I would definitely say is not that he would be proud, but he would say, essentially, we are now addressing what he has been addressing in the past. So Jan Willems' approach of behavioral system was at a much earlier time. And as you all know, or at least you, Marco, know, he developed that in the 80s of the last century. So very long ago was essentially a database control framework that we are having. And I think I commented on that also at the very beginning, saying that we are talking about philosophy. And the key is really, what are the tools? Are we dealing with in that respect? And that essentially answers your second question. You said, okay, what's the difference between what I showed you here, or on Friday, Claudio was showing you, to system identification? Well, the difference is the object of how we represent our dynamical system. It's not so much whether we call it data-based, or whether we call it state space, or whether we call it frequency domain, or whatever we want to call it. It's more, what is the object? And the object that we are now having here is a different mathematical object. Namely, we don't have a differential equation here anymore. And that is the key feature. So this is the same step that we had between frequency domain and time domain formulation, just that now we can stick to the time domain formulation. So it's the answer to that, what's the difference, is, I think, not asking what's the difference, but it's a different approach, allowing us, same as state space, frequency domain, now we have yet another representation, and they are not in competition, as we know. Also, frequency domain and state space, you jump back and forth, you use whatever is the best suited to deal with your needs. And we will see that also in the future with the approach that we are having here. And again, that is only one approach. So this only holds for the first part of my talk. So I think it's more a question of philosophy, and I agree, it's more a question of the tools and methods how we deal with this kind of things. We have a different representation of a system. It's still a system. It's still dynamics. Everything that we have holds. Now, of course, we need, that was your third question, essentially. So why are we talking about the same things here that we are talking about in the classical way? Dissipativity, LQR controller, H infinity, I mentioned, it's all the same things that we had before. So why doesn't here a new data-based approach lead to completely different new things? And the reason behind that is exactly also that. So that's the answer, or my answer to your third question. So we essentially have the same object with the same kind of properties, and we get inspired by those. And that's a beauty, right? That we can talk still about dissipativity, and that we can talk make relation to what we know in our system, now using different mathematical tools. So it's again the same answer, saying we have now a new framework, but the key concepts, the consequences, the properties, the important things for our control systems are still the same, as they did not change when going from the frequency domain to the state space world in the 60s. And now to your four-tank question, the last one, that was a real question, and there you are obviously right? So if you have a nonlinear system and you use a linear method, as I did in my first part, to just pretend that the nonlinear system is linear, that is bogus. But that's essentially what we always do, right? Whenever you have a linear controller design method and you apply it to a real world system, your real world is always nonlinear, right? And so there is no reason to believe that this works. At least I addressed it in the next step, in that I said the key feature here is really that we have robustness, and this noise robustness towards noise. This is something that makes this practical. And that's the reason why it worked at the very beginning for the four-tank system, why a linear controller, plain vanilla, works for a nonlinear four-tank system. It's a robustness kind of consideration. And in the next step, when we talked about nonlinear MPC, then we exploited that explicitly to come up with guarantees. So I hope that answered those questions. I guess we need a glass of good Italian wine to discuss further depth of whether we have a new theory here or whether it's just old things that are labeled with new names. The point is, we should not see it as a competition, but we should see it as an addition that we let develop. And in 10 years or so, let's have a look at how things develop and whether this is now something that stands on the sides of frequency domain, state space, and so on as yet another representation of a system, how you can deal with systems, or whether it goes away like many of the things might go away. Long question, long answer. Too long summer school presentation. I very much apologize.
Thank you.
Okay, then I guess since we're already quite evolved in time, I would like to thank Professor Allgöwer very much from the side of the organization team of the summer school for this fantastic presentation, and also all the audience for the interesting questions. And we will take the lunch break now and come back then as on the schedule on the homepage for the student presentations. And then later in the afternoon, we have Stephen Wright giving a second kind of expert talk later in the afternoon. I hope to see many of you back.
Thanks everybody for listening. Bye-bye.
Many thanks.
Good luck for your PhD projects.
Thanks.